Hello, welcome back to General Chem Chapter 7 for the MCAT grind. This is going to be a quick one about thermochemistry because we covered it pretty similarly in the physics section. So this equation of energy conservation, the net universal energy is equals to the heat gain minus the work put out by the gas and the system, right? So heat in is positive and the work output generated would be, taking away the energy, so Q minus W. And you can refer back to the physics section where we know that if there's no heat added in, right, then it would just all depend on the work being put out. Net U equals to negative W. And you can think of other functions such as if volume is constant, net P changing V, so there's no, if no change in volume, then there's no work done, so it's only determined by the heat. We can also use this equation, constant PV calorimetry, where the pressure and the volume is constant. We use Q equals MCAT, where heat added in equals the M, which is the mass of the object, times the specific heat for the substance and the change in temperature. So this is in joules. So mass times the specific heat in joules per kg in kilogram Kelvin, and then times the changing temperature, which can be Kelvin or Celsius. It really doesn't matter because it's just a change, right? It's an arbitrary number. So this is in joules per kg, pretty much, in a specific heat. For water, it's 1, exactly 1. So you just need to know that for 1 cal every joules, or 4.1, around 4.1 joules equals to 1 cal. We also have the standard heat reaction, which just equals to the final product minus the reactant. So you need to know the enthalpy change for all the net finals minus the initial reactant. So think about an equation, putting multiple equations together. For example, you have a general carbon, the combustion of a reactant that may need a certain amount of heat released, and if you were to pair that with another reaction, you can see what's the net energy gain or what's the net energy loss. We can apply the same principles to bond energy, where energy is inputted to break a bond, and when bonds are formed, they release energy. So to reiterate, it's endothermic to break bond, whereas it's exothermic to form new bonds. And you can use those numbers to add up and to see what's the net gain by the molecule of energy of if there's more bonds formed. That's generally increase in energy. And if there's less bonds formed, then that's typically an exothermic reaction. But it could also depend on the type of bonds. For instance, double bonds are harder to form, right? Create more energy to form rather than single bonds. We also have the concept called entropy or randomness, where entropy is determined by the reversible Q divided by the temperature, and usually it measured in joules per mole K. So in joules every mole K. So it's joules per mole K. That is the standard for entropy, and that can be measured as increase or decrease, and in the same way as we measure enthalpy, the product minus the initial. So net product minus the net initial. And all of the universe entropy is always increasing. So if you have a system, think about you're stacking up blocks, you're making them more ordered, but you require external energy input, right? My arm, rather than being random everywhere, you're fixing them to move this. So the overall, this becomes more ordered, so is more ordered, so decreasing entropy for this system. But for the big grand scheme of things, because I'm moving more air molecules around this area, moving my arms, that increases the randomness. Okay? So it's a weird concept, but it's there to grasp. The reaction quotient of the Gibbs free energy is given by this equation, like earlier, is enthalpy minus temperature times the entropy. is Gibbs free energy state. And it can also be determined using R, which is the gas constant, 8.3145 joules per mole K, or 0.083 LATM. So times ln K. K is the equilibrium. So if you have equilibrium, then that should be 1. So just negative RT ln equilibrium, and it should be, this shouldn't have any change. But if you have a subsequent change in equilibrium using Q, right? Remember the Q from the equilibrium chapter where it's products over reactants, and if it's product favored, then Q is going to get higher, right? So it's going to shift this reaction and make the G, delta G, and shift the equilibrium. Okay, that's what we mean to shift equilibrium. So in a forward reaction, G typically is negative because it wants to be more energetically favorable, so negative G. And if it's product, there's too much more product, so it gets heavier, so that's going to shift more towards the left, and that means the product is going to get more, add more RT ln K. So this is going to be more, add more positive and make delta G overall more towards 0. And when it gets positive, then the reverse is spontaneous, and the forward becomes non-spontaneous. Hopefully that makes sense.